In this lesson, we are going to talk about chemical calculations. So we start by the atomic mass, the average atomic mass. We'll talk also about the formula mass, mole and molar mass, and we finish by the percent composition of compounds in elements. As learning objective, at the end of this lesson, we'll be able to understand the meaning of the atomic mass unit and also to understand the concept of the average atomic mass, also to have an idea about the mole, the molar mass, and how to differentiate between the atomic mass and the molar mass, and we finish by the percent composition of element. First, the atomic mass. So the atomic mass is the mass of an atom in atomic mass unit, AMU, on a scale where the carbon or the isotope carbon 12 is a reference point. So here on this scale we can say that one carbon isotope carbon 12 atom has a mass of exactly 12.0 atomic mass unit. So the carbon atom is defined as having a mass of 12.0 atomic mass unit. Or in other terms, we can write like this: one atomic mass unit is defined as the 12th of the carbon 12 atom. And from this definition of the atomic mass unit, all the masses of the other elements were determined. So of course in atomic mass unit. So the other masses that we have here we have these isotopes: boron 10, boron 11, carbon 13, oxygen 16, the two isotopes of the bromine. All these were determined in relative to this definition, to the carbon 12 isotope. Now two questions arise from this definition. The first one is, why did we introduce this unit? So why didn't we use the mass of the atom in grams? So why don't we use the grams unit? The answer is that the mass in grams of the atoms is extremely small, so it is difficult to calculate or to work with this type of masses. For example, the mass of one atom of hydrogen is about 1.6735 times 10 to the minus 24 grams. The magnitude of this mass is extremely small. Also, the mass of one oxygen atom is about 2.6561 times 10 to the minus 23 grams. We can see how extremely they are. So it is challenging to work with this type of masses, but instead it's better to work with atomic mass units. In atomic mass unit, the hydrogen atom will have a mass that is easy to handle. The same thing with oxygen. So this for the first question. The second question is, here we have an extract from the periodic table, and as we have seen in the previous lesson, on each cell we have the chemical symbol of the element. Above this element or this chemical symbol we have the atomic number. For example, here we have the nitrogen, we have 7, and oxygen we have 8, and just below we have the mass number. So this mass number in the periodic table, this mass number, what does it represent? Since most of the elements exist in isotopic mixtures. For example, the boron exists as mixture of boron 10 and boron 11 with different abundances. So this mass for boron, that is 10.81. Does it represent the first isotope or the second? The same thing for the oxygen, because it has 3 isotopes. So this mass number, which represents the first one, the second one, or the third one? And the same thing for the other elements. The answer is that this mass number is just an average atomic mass. So this average atomic mass is determined from the isotopic mixtures. In order to calculate this average atomic mass, we take into account the mass of each isotope and the relative abundance in order to calculate this average atomic mass. But this term average, we don't use it a lot. Just we say the atomic mass, which means the average atomic mass when we take the mass numbers from the periodic table. So they are average atomic mass, but we just say atomic mass. For example, we have 2 types of elements. We have the chlorine and the magnesium. So we are asked to calculate the average atomic mass of these isotopic mixtures. We start by the chlorine. How do we calculate this atomic mass? So we have to introduce the relative abundance for each chlorine. We have for chlorine 35, we have 70. So we have the relative abundance of chlorine 35 over 100. So here we have a fraction of 1 times the mass of the chlorine 35. Here it is the mass in atomic mass unit. Plus we have the relative abundance of the chlorine 37 over 100 to get the fraction of 1 times the atomic mass of the chlorine 37. So here also it is in atomic mass unit. So if we replace here, we have 75.53. So it will be 75.53 over 100 times the mass of the chlorine 35, which is 34.97. Plus the same thing here, we have 24.47 over 100 times the atomic mass of the chlorine 37. So here we can see that the first part represents the chlorine 35 and the second part we have chlorine 37. So here we have the atomic mass. Here we can say the average atomic mass. So this equation will be is composed of 2 parts. If we have 3 isotopes, 3 parts. If we have 10 isotopes, it will be composed of 10 parts. Making the calculation, we get a value of 35.46 atomic mass unit, because here we have both value in atomic mass unit. And the same thing for the magnesium. Here the magnesium we have 3 isotopes, the isotopes 24, 25 and 26. So we do the same thing. Now the magnesium. So the average atomic mass of the magnesium is obtained from this. So we have the relative abundance of the magnesium 24 times the atomic mass of the magnesium 24 plus the relative abundance of the magnesium 25 times the atomic mass of the magnesium 25 plus the relative abundance of the magnesium 26 times the atomic mass unit of magnesium 26 divided by 100. And if we replace each term by its value, we'll get a number, and here we have in atomic mass unit, and in atomic mass unit. And by replacing each term by its value, we get a value of 24.31 atomic mass unit. So here is the average atomic mass of the magnesium that we find in the periodic table. Now let's talk about the formula mass. So what is the formula mass? It is the sum of the atomic masses in atomic mass unit of all the atoms present in a chemical formula of a compound. For example, here we have this compound. We have the AlOH3, the aluminum hydroxide. Here we have this chemical formula. In this chemical formula we have one atom of aluminum, and we have one atom of oxygen and one atom of hydrogen. But here we have this parenthesis. So here 1 oxygen times 3 and hydrogen times 3. So we have in reality 1 atom of aluminum and 3 atoms of oxygen, 3 atoms of hydrogen. So how do we calculate this formula mass? We use the average atomic masses from the periodic table. So the average atomic masses that we have calculated here, we use them to calculate the chemical or the formula mass. So here each atom has its average atomic mass. For example, the aluminum, it has an average atomic mass of 26.98. So we replace here. The same thing for the oxygen. It has an average atomic mass of 16, and the hydrogen, it has an average atomic mass of 1.0. So we replace here, and here of course we have to multiply by 3. So here, for example, we have 1, 0, 1, or here we have 16.0 times atomic mass unit times 3. The same thing here, atomic mass unit times 3. So here at the end we make this sum and we get the value of the formula mass, which is 78.01 atomic mass unit. So here we have the mass of one compound of aluminum hydroxide. So we can see that we get first we use the atomic mass, the average atomic mass. We get them from the isotopic mixtures, from the isotopes. So we use the mass and the relative abundance of the isotopes to calculate the average atomic mass, and from this average atomic mass we can calculate the formula mass in atomic mass unit. So here it is important to determine first the average atomic mass of each atom, and after that we can calculate the formula mass. So in periodic table we have the average atomic mass that are easy to use. But if we don't have this periodic table, we have first to start by calculating the average atomic mass from the mixtures, and at the end we get the formula mass. As example, we have to calculate in this second example the formula mass of each of these compounds. The tin fluoride or the SNF2, and the Na2SO3, and this compound, which is a chemical fertilizer for crops that we call urea. So we start by here we have the example 2. We start by the SNF2. So we get this. We have here this table. Here all these are atomic masses that are obtained from the periodic table, which means that they are average atomic masses. So here we don't have to look for the mixtures of isotopes, but the average atomic mass are ready to use. So to get the formula mass of the compound, we have the atomic mass of SN plus the atomic mass of fluorine, but here we have times 2 because we have 2 fluorine atoms, and we replace, we get a value. So these are the values. So fluorine is 19 and tin is 118.71. we have a value of 15671 atomic mass. So it is 156.71 atomic mass unit. The same thing for the second compound, which is Na2SO3, or the sodium sulfite. Na2SO3. Its formula mass is equal to atomic mass of sodium times 2 plus atomic mass of sulfur plus the atomic mass of oxygen times 3. So here we have 3 atoms of oxygen. By replacing by this value, we have the sodium 23, oxygen 16, and sulfur 32. We get a value of 126.04 atomic mass unit. So all these values are in atomic mass unit. The last one, it is the urea. It is the NH2, 2 times CO. So its formula mass is equal to, we have the atomic mass of nitrogen plus atomic mass of hydrogen times 2, but here we have 2 times this substituent. So here we have times 2 plus the atomic mass of carbon plus the atomic mass of oxygen. So we get a value of 60.06 atomic mass unit. So these are the formula mass of each of these compounds using the average atomic masses from the periodic table. Here again, we don't need to add each time the average, because from the periodic table all they are average from the isotopic mixtures. Now let's talk about the mole. So the mole is the amount of a substance that corresponds to the number of atoms in exactly 12 grams of the carbon-12 isotope. So here, when we talk about the mole, we are talking about an amount of substance. An amount of substance. So for example, here we have exactly a container that contains exactly 12 gram of carbon 12 isotope. So in this mass, in this weight of 12 gram of carbon 12, we have, it is defined as this mass, it is defined as 1 mole. So 1 mole corresponds to exactly an amount of substance that is contained in 12 grams of carbon 12. What does it mean, this 1 mole? This 1 mole, it means that we have a number of carbon 12 atoms. So in 12 grams of carbon 12, we have, it corresponds to a quantity of 1 mole. And in this 1 mole, we have the number of carbon 12 atoms. For example, if we make just an analogy, we have a continent that contains several oranges. Here we have oranges, we have 5 oranges. So here we have, for example, 1 kilograms, okay? And in this 1 kilograms, we have 5 oranges. So here, the 1 kilogram represents, let's say it is equivalent to 12 grams of carbon 12. And here for this 5 oranges, it is the amount of this continent, which will correspond to the number of the C12 atoms. Here we have 5 oranges, and here we have a given number of C12 atoms. And this number is called the Avogadro numbers. Okay, so the Avogadro's number, here we have the Avogadro's number that is symbolized Na. It is always equal to this value. We have here 6.02 times 10 to the 23. Here we say objects. So objects, it can be anything. For example, here objects, it refers to carbon 12 atoms. So here, in 1 mole of C12 carbon 12 isotope, we have a number of exactly 6.02 times 10 to the 23 of carbon 12 atoms, which is a huge numbers, because we have billion of atoms within this 12 gram of carbon 12. For example, here in this figure we have this first one on the left, we have 1 mole of carbon. In this image we have 1 mole of copper, and here we have 1 mole of iron. So here we can see what is the mass of 1 mole of iron and copper and carbon. And inside each of these pure substance we have exactly this number of atoms. For example, in this sample of copper we have 1 mole of copper, but inside this pure substance we have this number of copper atoms. The same thing for the iron atoms. We have this number that corresponds to this mass of iron. So let's do the example 3 for a better comprehension of this concept. So example 3, we are asked to calculate the number of atoms in each of these quantities. For example, we have 4.1 moles of copper atoms. So how many atoms are there in this quantity? So we have a quantity of, here we have copper. We have copper inside. We have copper. And in this copper we have an amount of substance that is equal to 4.1 mole of copper. We have 4.1 mole of copper. So we are asked to determine the number of copper in this container. So here we will use the dimensional analysis to resolve this problem. So we have a given value. We start by this given value. We have a number of moles, a quantity, and we are asked to determine the number of objects. What conversion factor should we use to go from the moles to the number of, let's say, objects? We use the Avogadro's number. Why? Because the Avogadro's number that we have here, it relates the amount of substance to the number of objects. So what does it mean, Avogadro's number? It means that in 1 mole of any sample we have 6.02 times 10 to the 23 objects. Or we can write it in different manner. We can say that 1 mole at the bottom, 1 mole of a substance, it contains this value, this number of objects. So here we have two conversion factors. We have this one and this one. Both are the same, but they are written differently. We have a beginning value of 4.1 moles of copper. So we have to multiply by conversion factor that will give us the number of copper. So we'll use this conversion factor, this one. Why? Because the number of objects are written on the top of the fraction. So here we have 1 mole of copper atom that contains 6.02 times 10 to the power of 23 copper atom. So here we can cancel mole of copper, and we get the number of copper atom, which is equal to, so let's do the calculation. .46 times 10 to the 24. It is a positive exponent. So it is 2.46 or 47 to round up times 10 to the 21st. So we have this number of atoms. And the same thing with the other quantities. We multiply 1.5 moles of oxygen times the number of atoms using this conversion factor. Now for the number of oxygen atom, we have 1.5 mole of oxygen atom times 1 mole of oxygen atoms that contains 6.02 times 10 to the 23 atoms of oxygen, and we get the value. And the same thing for the number of glucose atom or glucose molecules. Here we can see that we can apply this method to determine the number of objects either for the atoms or for the molecules. Here we have 3.2 moles of glucose molecule times 1 mole of glucose molecule that contains 6.02 times 10 to the 23 glucose molecule. So here we cancel mole oxygen, and we get a value of 1.5 times. So we get a value of 9.03 times 10 to the power of 23. So atoms of oxygen, and here we have 3.2. So here we have 3.2 times that we get 1.93 times 10 to the power of 23 or 24 glucose molecule. So each time we were able to determine the number of objects, here atoms or molecules, in this quantity. So we used this. So here from the amount of substance we can get the number using the Avogadro's number, which is always equal to this value, 6.02 times 10 to the 23. Here it is. Now, after having talked about the mole, now what is the mass of a mole? So we know that a mole is a number. It is an amount of substance. It is a quantity or a number of objects contained in an amount of substance. Now, what is the mass? And of course, when we talk about the mass, here we are talking about the mass of atoms. So objects can be atoms or molecules on the atomic scale. So when we talk about the mass, for example, we have 1 mole of copper that contains 6.02 times 10 to the 23 atoms of copper. The same thing when we talk about 1 mole of iron. For example, in 1 mole of iron we have the same quantity. We have 6.02 times 10 to the 23 atoms of iron. But if we measure the mass of this number, if we get a mass, and the same thing if we measure the mass of this element, the question is if these two masses will be equal or different. The answer is it will be different. Why? Because elements are different. Each element, it has a number of protons different from the other. And we have seen before that the mass of elements is determined by the number of their nucleons, that are the protons and neutrons. So even if we have the same number of neutrons, but the protons are different, each element has its own number of protons. So obviously their masses will be different. So even if we have the same number of objects, but the masses will be different. So the masses of all the elements is different. So the mass of 1 mole of element, that we call sometimes molar mass, varies and is different for each chemical substance. So for each chemical substance, for example aluminum, it has a molar mass, let's say 1. And for oxygen it has a molar mass 2. For nitrogen it has a molar mass 3. All these molar mass are different. Okay? And the molar mass is here. What is the value of the molar mass? Now what is the value of the molar mass? The value is in grams. Okay, so the molar mass is the mass in grams that is numerically equal to the substance atomic mass. So we have the mass, the molar mass in grams. It is numerically equal to the atomic mass unit of a substance, of a given substance. So the molar mass is the mass in grams of a substance numerically equal to the substance atomic mass. For example, we have seen before that the chlorine has an average atomic mass equal to 35.46 atomic mass unit. So which means that this, we can write it like this: 1 mole of chlorine, it has a mass of 35.4546 grams. The same thing for the carbon. We have a carbon 12 for the isotope carbon 12, which is equal to 12 atomic mass unit. So 1 mole of carbon 12, it has a mass of exactly 12.0 grams. Here we have the definition of 1 mole. Okay. Also, for oxygen atom, it has an average atomic mass of 16.0 atomic mass unit. Here we have 1 oxygen atom. But if we have 1 mole of oxygen atom, its mass will be 16.0 grams. Say carbon dioxide. Okay, here we have carbon dioxide. It has an atomic mass of its it has a formula mass. So here for the atoms, and now for the molecules. Here it has a formula mass of, here we have the carbon plus oxygen times 2. Carbon it has an average atomic mass of 12.01 and oxygen is 16.00. So here both are in atomic mass unit, or okay, so we get here a value of 44.01 atomic mass unit. But here we have the formula mass for 1 carbon dioxide. So for 1 mole of carbon dioxide, we have a mass of 44.01 gram. Or we can write it differently. The molar mass of carbon dioxide is equal to 44.01 grams per mole. We can write it in a simpler manner, gram per mole, which is the concept of the molar mass.